So, today we will be talking about evolutes of a curve. So, we will assume that there is a curve r equal to r s, let me call it C. We are looking for a curve C 1 such that C becomes involute of C 1. So, our aim is to find a curve C 1 such that the given curve C is an involute of C 1, such that the given curve C is an involute of C 1, and that means C 1 becomes evolute of C. Consequently, C 1 becomes evolute of C. So, we are searching for evolute of a given curve C. Broadly speaking, this is what we will be doing. So, as usual, I will denote. So, let me assume that the evolute is given by the equation r equal to r 1 s 1. S and S 1 are the natural parameters on C and C 1 respectively. And throughout, as we did yesterday, we will be denoting the objects of C 1 by standard symbol with 1 as a suffix. So, so this is what we are searching for. This is the curve C 1. All right. So, geometrically, suppose I am giving this curve C and I am looking for another curve C 1, or let me draw little differently, because we need normal of the given curve. So, suppose C is this curve and the normal of this curve will coincide with the tangent of C 1. So, this is the normal of C at a point P, and we want that it should coincide with the tangent T 1 of C 1. This is the curve C 1. Suppose it becomes tangent over here at the point Q, and the origin of the coordinate frame is here. So, if I join P and Q with O, then I will be getting these position vectors O P and O Q. We may call these position vectors as R and R 1 respectively. If I get an expression for R 1, the job will be done in terms of the known quantities. All right. So, from the figure, you can see that P q, vector P q is equal to R 1 minus R, or I can say R 1 equal to R plus vector P q, and according to the hypothesis, P q is a normal vector. And what is a normal vector? Yesterday we considered a special case when the normal is actually the principal normal. This is a particular situation. More generally speaking, any vector which lies in the normal plane is a general normal. So, this time I will assume that the normal p q is actually the general normal. Normal plane, as I told you earlier, because there are 3 planes associated to every point of the curve. The plane which has the highest order of contact is called the osculating plane. The other 2 planes are called rectifying plane and the normal plane. So, a plane generated by the 2 normals, the principal normal and the binormal, is called a normal plane. Any vector in the normal plane will be termed as a normal vector. So, a normal vector is generated by what? Small n and capital N small b. So, this is R plus p q means some lambda times t plus mu times b. This is the general normal that we assume is the vector p q. So, this is R 1. Let me call this equation as equation number 1. Now, I have to determine lambda and mu. Once you get hold of lambda and mu, you get the expression for R 1 explicitly, because in the right side everything is known to us. So, we start computing lambda and mu. So, what we do? We differentiate this equation with respect to S 1. So, differentiating with respect to the parameter S 1. S 1 is the parameter of the curve C 1. So, R 1 derivative of R 1 with respect to S 1 will be T 1, the unit tangent of the curve C 1, and in the right side I will write down dr over ds into ds over ds 1 plus lambda and mu will also be functions of S. So, plus lambda dash derivative with respect to S into ds upon ds 1, t as it is, plus lambda times dt over ds into ds over ds 1 plus mu dash derivative with respect to S into ds over ds 1 and b as it is, and plus mu times dB upon ds into ds over ds 1. So, throughout I will take ds upon ds 1 common, and this expression dr over ds is t. This is going to be common throughout, and plus lambda dash into t plus lambda t dash is k n plus mu dash into b plus mu b dash means minus tau n. So, this is minus tau n, and outside you have ds over ds 1. All right. dt over ds is k n, b dash is minus tau n. Is everything fine? I think yes. All right. Now, let us simplify. Let us collect the terms of t, n and b. So, left hand side is t 1, and in the right side I have 1 plus lambda dash into t plus, look for the terms of n, lambda k minus mu lambda, lambda k minus mu lambda into n, and then plus you have only one term of b. Okay. So, this is mu dash into b ds over ds1. I hope we have computed correctly. And dash was not there. Oh, oh, this was not t, this was in fact n. I was calling it n and I wrote down this as t. So, that is the mistake here. So, I have to change it. This is not t, this is n. So, everything will change. Yes, normal plane means a plane generated by n and v, yes. So, lambda dr over ds, okay, lambda dash into t means n. So, this will be n plus lambda, this is dn over ds plus mu dash into ds over ds b, rest is okay. So, there will be change lambda dash into n, lambda dash into n plus dn over ds. So, this term will be changed, this is lambda and n dash is tau b minus k t. Plus mu dash into b plus mu, rest of the term are fine. So, let me change it. So, there is only two terms for t, one is here and the other one is here. So, we will be getting 1 minus lambda k into t. Okay, and then look for term of n. One term of n is here and the other one is here. So, lambda dash minus mu tau plus lambda dash minus mu tau into n, and then look for terms of b. These are two terms, one is here, another is here. So, lambda tau and then minus plus mu dash into b and then ds over ds1. Okay. I think we have written it correctly. 1 minus lambda k into t, lambda dash minus mu lambda plus tau lambda plus mu dash into b. So, this is number 2. All right, and then now since T1 lies in the normal plane of C, because T1 and these two are collinear. So, in fact, the term and therefore, comparing the coefficients. So, since T1 is a normal to C at P and it is collinear with PQ and it is collinear with PQ and PQ, if you look at PQ, it is lambda times n plus mu times b, which is equal to lambda times n plus mu times b. Okay. The coefficient of t must be 0. If you compare the two vectors, these two vectors are equal. So, this means, on comparing the coefficients in 2, you will be having 1 minus lambda k equal to 0 and this will give you lambda equal to 1 upon k. So, you get hold of lambda, and then over here what will you be getting? T 1 equal to this plus this. Okay. So, T 1 is actually lambda n plus mu b. Okay. So, lambda dash and lambda dash minus mu tau, it is equal to some scalar times lambda. So, let me call it alpha lambda. Okay. And number 2, lambda tau plus mu dash must be equal to some alpha times mu. No, same. In fact, what I am saying is that this T 1 is equal to alpha times the normal P q. Okay. This is what I am considering, and P q is what? P q is lambda n plus mu b. Okay. Right. So, now we have to solve these two equations. So, from the this is first, this is second, and this is the third one. So, second and third I will look for. So, second and third imply that lambda dash minus mu tau upon lambda is equal to lambda tau plus mu dash upon mu, and both of them are equal to alpha. Okay. Lambda dash minus okay, correct. Now, this I have to simplify. So, when you simplify, this will give you lambda dash mu minus mu square tau equal to lambda square tau plus mu dash into lambda. I will collect the terms of tau. So, or lambda dash mu minus lambda is plus minus lambda into mu dash equal to lambda square tau plus mu square tau. I have rewritten in this manner. Okay. And what it will give me? Tau is common in the right side. So, lambda dash, use the other pen. So, lambda dash mu minus lambda mu dash, okay, and tau I am taking common, mu dash upon tau. So, upon lambda square plus tau square, mu square, oh sorry, mu square equal to tau. So, tau, in fact, we usually look for torsion. So, at this point I will say that I have got an expression for the torsion tau. Okay. Okay. So, and this, can you simplify it? In fact, yes. So, this in fact no. In fact, this you can write down, this implies tau equal to d by ds of tan inverse lambda upon mu, yes. So, we can further simplify it and torsion comes out to be this much. Okay. Now, I can integrate both sides, integrating both sides with respect to s, of course. You will be having integral tau with respect to ds plus a constant, let me call that constant as a, equal to tan inverse lambda over mu, or I will say that tan of a plus integral tau ds equal to lambda upon mu. Okay. So, this gives you mu equal to lambda times cot a plus integral tau ds. Okay, lambda I already had in number 1. So, this becomes 1 over k into cot of a plus integral tau ds. Tau is known to us, and what we were looking for, mu and lambda. So, both these quantities which were unknown we have determined, and therefore, we have determined the equation of the curve C1. So, now substituting these values of lambda and mu into the first equation that you had, r equal to r1 equal to r plus lambda n plus mu b. So, substitute these values. So, substituting So, substituting the values of lambda and mu into 1, that was equation 1. Yes, we get the equation of the curve C1, and C1 is the evolute for the curve C. Okay. So, this gives you how to find out the equation of evolute of a given curve. Okay. Now, the other things are about finding its basic vector fields like tangent I have already worked out, principal normal and binormal. Once you get hold of these Freinet trihedron, you can work out the curvature and torsion for C1. So, this I leave as an exercise. Find Freinet trihedron and curvature and torsion for the evolute of a given curve. The computation will go on the same line as we did for involute. It is a matter of computation, nothing technical about that. So, I stop the first part of my lecture here. We will continue about the surface in our follow up lecture.